All right, so let's learn about magnetic field around the Earth. I think I talked about the Earth magnetic field when we're talking about Mercury and Venus. Anyway, in the third exam, most of you got that question answered incorrectly. So the Earth just have a good amount of magnetic fields around itself. So it's coming due to the liquid outer core in the Earth interior. So the source to have magnetic quality is due to the moving charges. So when we have liquid iron core, which is orbiting and rotating, so those charges are moving around, that will induce a magnetic field around the Earth. So there's a magnetosphere around the Earth, so we can stop the charged particles that coming from the solar winds reaching to the Earth's surface. So the solar winds are the charged particle waves that's emitted by the sun, right? So if we are receiving those, we will get health effects on our life. So this magnetosphere around the Earth is protecting us from receiving those solar winds. So around the Earth, there's a magnetic field. So as you see on this picture, this is the level, like the furthest level that the magnetosphere acts. So we call this as the magnetopoles. And so when the solar wind comes in, these magnetic field lines stop those solar winds comes into the Earth atmosphere. But you know, like all the way up in the northern pole and the south pole, there's a little opening where the let me tell you something. So these blue color lines represent the magnetic field lines that act around the Earth, and we call these as Van Allen belts. These are not the ozone layer. So I think most of you get confused between the Van Allen belts and the ozone layer. Ozone layer is a different thing. We'll talk about it in next slide. So Van Allen belts are the magnetic field lines that's protecting the Earth, receiving the solar winds. So as you see here, by the higher in the North Pole, there's a little opening, so the solar wind can enter in there, and those are entering into the Earth atmosphere, and it's get scattered around, and they are like orbiting around the magnetic field lines like a spiral, right? So when it is entered, it gets scattered and it creates colorful lights. That's what we are calling the northern lights, right? So near the northern pole, we should be able to see these color lights there. We call these as auroras, and that's happened due to the Van Allen belts intersect the atmosphere at all the way up in the North Pole. Also in the South Pole, the charged particle can collide with the atmospheric atoms. When they do, they create glowing light called an auroras. So maybe you have seen those. All right, so the next topic is plate tectonics. So not like Mercury or Venus, we have plate tectonics on the Earth. So as you see in this map, there are plates that's on the Earth that can move, right? So there are 9 major plates, which include North America, Pacific, Eurasian, African, Indo-Australian, Australian, Indian, and South American and Antarctic. So those are the major 9 plates that can move around. Okay, so the largest plate is the Pacific plate, and most of it's located under the ocean. So it's moving northwest at a speed of around 2.75 inches per year. So it's a very small distance, so we can't see it. But if you're living like millions of years, we can see these shifts. So there are also many smaller plates throughout the world. All right, so let's learn about the atmosphere. I think you learn about the atmosphere in the homework assignments that I gave you on Wednesday. So anyway, so this picture here, the one over here, we are not going into the Earth, we are going above the surface of Earth, right? So if we traveled like 10 miles, that's called the troposphere. That's where the life forms, and we have a weather condition that's livable, and that's take the 75% of the atmosphere. Then when we are moving away about 20 miles higher, then we have the stratosphere, which is where we can find the ozone layer. So ozone layer is protecting us from the UV light that's coming from the sun. So UV, that's ultraviolet light. Okay. So it is different from Van Allen belts. Van Allen belts are the magnetic field lines, but ozone layer is different. It's O3 layer that's protect us receiving the UV light. Then comes in the next 20 miles, it's the mesosphere. That's cold, and there are a few molecules, and shooting stars are traveling over here, and also it can burn up here. Then comes the thermosphere that goes 350 miles across, and there we have fewer molecules and high temperature fluctuation, so it can change the temperatures. Then come the exosphere, so it's go past 350 miles over here and then go all the way up to 29,600 miles. So occasional molecules gradually escaping into space. So where the gravitational acceleration over here all the way up is really, really small, so the things can escape into the space. So over here, we have the graph of temperature and the altitude. So we are going from the surface to high in the sky. So as you see here, this is the temperature curve. So you see like in the 10-kilometer range, it's the temperature is decreasing. Then again, it's increased. And over here, high in the sky, somewhere here in about 30 miles high, we have the highest temperature. Then it's reduced again and it rose again, right? So in the higher latitude, like passing about 50 miles, again, the temperature start rose, right? So on the surface, we have the highest temperature. Then when we are traveling high in the sky up to about 10 miles, the temperature decreases. Then again, when you're passing 10 miles, it increases again and decreases and increased again. Then if you think about the composition of air in our atmosphere, it's not only oxygen. So when we say like the atmosphere, we feel like it's all oxygen, right? It's really not. So we have about 78% nitrogen in the air and 20% oxygen and about 0.93 argon and 0.04 carbon dioxide. So if we have only this small amount, why are we worrying about carbon dioxide a lot, right? So we were talking about like how to reduce the carbon emission, the carbon dioxide emission, but we have very small amount of carbon dioxide. So we have the smallest amount of carbon dioxide between the other gases. So nitrogen is the highest amount of molecule type in the air, right? So the gas type in the air. Also, the atmosphere contain water vapors. So on average, around 1% at sea level and about 0.4% over the entire atmosphere. So if you think about this pie chart, you can think about like how much percentage do we have oxygen here, right? So oxygen is only 20%, but the argon, water vapor, carbon dioxide and other gases take only tiny bit here. But among all the other gases, the carbon dioxide has 0.04% and neon maybe 0.0018%. So anyway, so what is the Earth? Why is the Earth so warm, right? So there's a greenhouse effect acting naturally in the Earth's surface that heats up. So the greenhouse effect is a natural process that warms the Earth's surface when the sun energy reaches the Earth atmosphere, some of it reflect back to the space and the rest is absorbed and re-radiated by greenhouse gases. It's so very similar to the greenhouse plant over here. So when the sunlight enter into the plant, the sunlight get absorbed to things around here, and some percentage of the sunlight will emit away from this surface. But there's the energy that's absorbed, and those energy will get reflected back and forth depending on this cover here. So Earth atmosphere acts like this cover. So when the sunlight comes in to the Earth atmosphere, once it gets absorbed, some portion get reflected, but the amount that absorbed over here will get automatically re-radiating inside and creating the greenhouse effect. So when we talk about greenhouse effect, we always remember the carbon dioxide, but carbon dioxide is not the only greenhouse gas. Water, carbon dioxide, and methane are the main gases that affect the greenhouse effect on the Earth. So methane, when you talk about methane, the most amount of methane is emitted by the farm animals. Carbon dioxide nowadays, it's not by the trees, it's coming from the human activities. So the visible lights enter into the atmosphere and warms the Earth's surface. And the surface emits infrared light. So when you talk about infrared light, we cannot see it by our eye, but if you're using infrared detector, we can see those. So for an example, the snakes are using infrared to read the objects, right? So the greenhouse effect is responsible for making the Earth about 35K, means Kelvin, warmer than it would be if it had no atmosphere. So having the atmosphere and having the greenhouse effect is important. But the thing that's happening now is greenhouse effect is higher than what we need. So it's making the Earth temperature go high. So the visible light, when it passes through the atmosphere and warms the planet's surface, and then the atmosphere absorbs the infrared light that coming from the surface, and it's trapped inside and heats up the Earth atmosphere. So this represents the sunlight that we are receiving to the surface, some portion, a little bit of it, I mean, good ratio is reflected back into the space, but the one that trapped over here will be scattering around and emitting, like re-radiating inside. All right, so these are this table represent the greenhouse temperatures. So here the Mercury, Venus, Earth, Moon, and Mars. So we're going to compare it. These are the average distances, and this is the reflectivity. But now at this point, my main focus goes towards the greenhouse. So this is the no greenhouse average surface temperature. That means if we don't have the greenhouse effect, these will be the average surface temperatures of these planets. So for Mercury, it will be 163 Celsius. For Earth, it will be negative 16 degrees of Celsius. It's very cool, right? So, but this is not the real temperatures, because we do have the greenhouse effect, so it changes the temperatures. So these numbers represent the surface temperature of each planet without the greenhouse effect. Venus is the interesting one. So here, if there's no greenhouse effect, the temperature is negative 40 degrees Celsius. Now, if you go to the actual average surface temperature, look at this. Mercury does have, in the daytime, it's 425 Celsius, but in the nighttime, it will be negative 175 degrees Celsius, right? And then on Earth, current, like with the greenhouse effect, the surface temperature is 15 degrees Celsius. And the greenhouse warming, the effect that came from the greenhouse effect is this much. So on Venus, the greenhouse effect is really, really crazily high. So the temperature differences that's given by the greenhouse effect is 510 Celsius. On Earth, we get about 31 degrees Celsius difference from the greenhouse effect. So when we are emitting more carbon dioxide, more methane and water vapor, then we are eventually increasing this number. All right, so these are the major greenhouse effect gases. So carbon dioxide, methane, water vapor, and nitrous oxide. So all these gases are naturally present in the Earth's atmosphere, and it's needed to be there to have the greenhouse effect to maintain the temperature, I mean the Earth atmosphere temperature. But as I mentioned earlier, we people are producing more than enough. So it's creating more greenhouse effect and increases the surface temperature over here on Earth. So the origin of the greenhouse effect is coming radiation and interacting with molecules. So in the ultraviolet range of the electromagnetic spectrum, molecules dissociates and create energy. Then in the infrared, the molecules vibrates. So if you imagine two molecules like hydrogen, like if you think about carbon dioxide, so we have carbon atom and two oxygen atoms. So blue color one represent the carbon, and let's say the red one represents the oxygen. So we have carbon and two oxygen molecules here, I mean the atoms, and they vibrates. So in the vibration, it's emit energy out. So that's in the infrared level. And when we go to the microwave in the radio spectrum, we get molecule rotate. So this rotates around and create the heat. All right, so the runaway greenhouse effect. So the Earth, let's say Earth is moving to the Venus orbit. So more intense sunlight, it would raise the surface temperature by about 30 degrees Celsius. So the runaway greenhouse effect will be there. So high temperature increases evaporation and warmer air and holds more water vapor. It increases the greenhouse effect, and it will increase the surface temperature. So resultant will be oceans evaporate and carbonated rocks decomposes and it releases carbon dioxide. So we get carbon dioxide by the carbonated rocks that's on the ocean beds. So when the ocean evaporates, this will be more active and it's emitted carbon dioxide. So Earth will be hot as Venus. So it will be dried up and will be look like Venus at one point. So the runaway greenhouse effect would account for why Venus has so little water. So on according to the table that we saw earlier, the greenhouse effect on Venus is really high. So it's evaporated the light, I mean the water. So why does the Earth climate stay relatively stable? That's because of the carbon dioxide cycle. So atmospheric carbon dioxide dissolves in the rainwater. Then the rain erodes the minerals that flow into ocean. Then the minerals combine with carbon to make rocks on ocean floor. And the subduction carries carbonate rock down into the mantle. And the rock melts in mantle, and carbon dioxide is outgassed back into the atmosphere through volcanoes. So that is the carbon dioxide cycle. It's very similar to the water cycle, right? So the carbon dioxide cycle is really important as well. So the Earth thermostat. So if we increases the greenhouse effect, that will strengthen the greenhouse effect and it will warm up Earth. And if we reduce the greenhouse effect, it will affect in cooling down the Earth, right? So there's a balance in the Earth atmosphere carbon dioxide cycle. So there should be a balance in there. If you break this balance, it affects the climate changes a lot. So the cooling allows carbon dioxide to build up in the atmosphere, and heating causes rain to reduce the carbon dioxide in the atmosphere. The burning of fossil fuels and rapid deforestation is raising the level of carbon dioxide. So here, carbon dioxide percentages over the years. So as you see, over the years, it's increased. And the good example is what is currently happening in China. Because of the COVID-19, there's a big effect on the carbon dioxide percentages in the atmosphere. I'll show you the data really quickly. But anyway, this is a picture of carbon dioxide that's concentrations change over 1 year. So if you look at this diagram here, the simulation, Let me open it. Maybe I have to share the other screen with you. Okay, so if you watch carefully, just observe it. So this red color things are the carbon dioxide. So carbon dioxide over the years, that's increasing, that's highest, right? So it's building up over the years, but we have an atmosphere to circulate this carbon dioxide around the Earth. So here, this is, I think, China area, right? So this is China region. So we have carbon dioxide gathered around here. And it's shifting out to over here, like higher in the northern hemisphere, and it's moving around the Earth. So over the years, it's developing up. So anyway, so it's so interesting to see like what's currently happening in the atmosphere. So this is the radar pictures that's collected over the region of China. So here, with the effect of COVID-19, how it's impact the carbon dioxide emission. So this is January 2019, and that's the January 26th. And then this is February. So February 2nd and February 9th, they had the highest impact of COVID-19. So they reduces the human activities, and that's reduces the carbon dioxide emission. Now here, back again, it's slowly like in end of February and beginning of March, they had COVID-19 affecting them. So the carbon dioxide emission is very, very minimum. So it's reduced in the atmosphere, but now they are recovering from that virus and they are coming back to action. So human actions started. So you see like the carbon dioxide emission backing up again. So that's what's happening there. So it's really important to maintain our carbon dioxide cycle to keep the Earth atmosphere in the good condition for human life. All right, so even a small temperature rises might cause us a change in sea level by melting the ice caps. So here, as you see, over the years, this red curve represents the temperature changes. So its rise, this red curve represents the ocean levels, right? So over the years, as you know, the temperature's gone up, and as you see, the sea levels rose as well. So it's due to the temperature changes, it's changing, but with the increase of temperature, it's always sea levels are rising. All right, so this is another cool picture to see. So this is a earlier picture, and this is the current picture. So you see like there's no glaciers over here, it's all melted out. All right, so please answer the questions below, and that will give you the participation credit.